All right, hello 130 students. I'm back to talk about adding two-dimensional vectors, but with numbers. So we looked at it before in drawings, and now we're going to look at it with numbers. So we'll talk in terms of positions again. So let's say we've watched an object, and we know where it is at a couple different times, or either what we'll know is where it was at the beginning and then how it changed its position from one place to the next. But now, so let's say we have a position 1 that looks like this. So it's at a position originally that's up and to the right from our reference point. We're going to call this guy R1. Just hook these together. Alright, so remember we use R for a position that's not pointing straight horizontal or vertical. So X is for horizontal positions, Y is for vertical, and then R is for that sort of total position, which is pointing off at an angle. Let's say it starts up there and then it moves down and to the right. So we have a change in position vector or displacement that points down and to the right. And then we're going to grab this guy. That is our delta R1, 2. So our change in position from time 1 to time 2. And this lets us ask our question, where is it going to be at time 2, and get an answer. So one way to do that, so that's a vector addition problem. If I want to know where it is, so let's come down here. If I want to know where is it going to be later on, that's to ask, when I add R1 to delta R1, 2, what do I get? What I'm going to get is R2, but what is that? All right. So graphically, we could use our tip-to-tail method. So we would take our two vectors. We would say I'd take our first vector, that's rule 1, just put it somewhere. And then I take the second vector and take its tail right to the tip of the first. So I put those together like that. And then if I want to know what the sum is, I draw my final resultant vector that starts at the base, the tail of the first vector, and goes to the end, the tip of the second vector. So I know, in fact, that this is what R2 should look like, this guy here. So yeah, R2, there you are. Should be these boxes smaller. So we know if we start at this position was up and to the right from the reference point, and then we move down and to the right, we'll end up at somewhere that's still up and to the right of the reference point, but quite a bit more over than it is up. So we have sort of a graphical depiction of what our second position is, R2, but we now want to get numbers onto this thing, you know, how far over it is. And then if we're talking about numbers, we might be thinking about an angle as well. That means we are going to need to know a little bit more about both of these vectors as well. So for starters, let's say we know that R1 has a magnitude of 10. So it starts a distance of 10 centimeters away from the reference point. And let's say that the distance it moves after that is 5. So this arrow is 5 long, 10 long, this is 5 long. One thing you could do with those two numbers is add them together. But do we think that this vector here is 15 centimeters long if these are 10 and 5? Well, no. In order to get the two vectors adding up to 15, they would actually have to be oriented like this. So if I took these two vectors, had them pointing in the same direction, and then added them together, then that result would be 15 long, and you can see that this vector is in fact, oops, you can do this, there you go, quite a bit shorter than what I get when I line those two vectors up together. So since we're adding together two things that are not actually pointing in the same direction, the sum does not have a magnitude that is equal to the magnitude of the two vectors added together. We saw that in the one-dimensional case. If I have 5 to the right and 7 to the left, the thing I get when I add them together is not 12. It's minus 2. So what can we say? Well, what we tend to do now, we got to recognize the fact that we're working in 2 dimensions here. So when we think about our vector r, we often think about sort of creating a coordinate system and breaking it down into the sideways and the up-down parts. The sideways being called the X and the up-down being called the Y. And so we make a right triangle out of this guy. So we think about, well, how could I get to the same spot up here? This goes back to sort of the instructions you might imagine for telling someone where a point is from our first lecture here. How do I get to this point? Not by going straight, but by going sideways first and then up. So I'm going to draw some new arrows. So think about starting here and going straight over until I get right underneath the tip. And then I'll draw one more. Starting here and going straight up until I get to the tip, and I'll scooch that over. All right. So now we made a triangle. What are these things? So this is R1. Let's see. Yeah. Then this little guy down here is X1. No, don't be capital. Oh, yeah, wrong. Phew. So this is X1. It really just wants them to be capitalized, but we don't. Okay. X1, that's the horizontal component, as we call it, of R1. And then what is this guy? This is Y1, the vertical component. And then to fully define this vector, we also need to know one more thing. Well, what's the angle? What's one of the angles in this triangle? So let's say we know in this case that we have a 60-degree. Get our symbol in here. Ha! So we have a 60-degree angle in there in this case. We can find the angle symbol. 1 second. There it is. All right. So we have a 60-degree angle from our triangles. Then we can repeat that same process. We look at our other vector here, delta R1, 2. Well, this has two parts as well that I can make into a right triangle. In order to get from here to here, though, I actually don't go in the same direction. So for the vertical part, I'm actually going to start by going down. Yeah, of course, it doesn't want to go down. That's fine. And then we go over to the right from there. Oop, pictures. Good Lord. All right. So we have our two components now of this vector. This horizontal component now is x2. And our horizontal component is y2. And then we need to know an angle in this triangle as well. Actually, made little angles here. I'll pull this in. Oh, why are you together angles? There you go. So I got an angle in this triangle. So we often use the Greek letter theta for angles. Well, but we're not going to because it's being annoying. I don't like it. All right, so let's put this in here. Let's say we have an angle of 30 degrees in this triangle. Okay, so we can think about these components you get by making these right triangles, the horizontal and the vertical components of each of these things. So how are those relevant? Well, when we go back to think about our addition, we see actually that the kind of simple addition that we could not do with the magnitudes, these numbers 10 and 5, we actually can do with the horizontal and the vertical components. Because we can do the same thing for R2. Okay, we wanted to find R2, so R2 we could make an arrow to the right, that's the x component, the horizontal component, and an arrow up, which would be the y component, the horizontal component. But now we'll actually see, if I say, well, if I do this first and then this, how far do I have to go sideways? I can take individually and say, well, first I do this, and then I do this. So if I add up the horizontal components, they actually add up to the correct value for the horizontal component of the sum. And then, interestingly, if I do the same thing with the vertical components, I first go up, and then come back down, we get the same thing. We actually get back to that right place. So while we can't use a simple sort of math equation, this, remember, has to be a vector equation. But if we treat it as two equations, one for the x component and one for the y component, then these do work in that simple way mathematically. So here's our first equation, and then we add another one, but that should have worked. Okay, fine. Y sub 1 plus delta y 1, 2 will equal y 2. And this should have a 1 as well. So we say, it's simple to add vectors with numbers because their components add up in the simple way that numbers normally add. But in order to do that, we actually have to go back and figure out what those components are first. So let's do this. Bring our components back home. So here's our x1 and our y1. Here's our x2 and our stay home, and our y2. So we have to take a triangle like this and figure out what these two sides are. But hopefully, if you looked at the math quiz, you familiarize yourself. There's a brand of math that deals in sort of exactly this kind of thing. I've got right triangles, and I know some information about it, and I want to get the rest. And that's trigonometry. So here we've got a triangle where we know an angle, and we know the longest side or the hypotenuse, and we want to know what the other two sides are. So then we can get into using, don't do that, okay, some of our trigonometric equations. So if we look at this guy here, we want to think about the trig functions we might use. So that's our SO, cot, TOA, sine, cosine, and tangent. So let's talk about SO first. That's the SOH. So this says the sine of an angle is equal to the opposite side divided by the hypotenuse. So if we look at that, is that going to help us get one of the things we want to know? Well, the angle we know, the opposite is one of the things we do want to know, and the hypotenuse we know, so we can use that little equation to find this guy. So what was that equation? So the sine of our angle, which is going to be 60 degrees in this case, is going to be equal to opposite, which is y sub 1, divided by the hypotenuse, which is 10 in this case. And then we can say, okay, I want to find y1, so I'm going to solve this algebraically. I multiply both sides by 10, and I get that y sub 1 equals 10 times the sine of 60, or 8.66. So we can actually go in here and say, this guy is 8.66. But not in a subscript. There we go. One thing we need to think about here, as we did in one-dimensional adding, is signs, positive and negative. So typically what we want to do is assign for both of these directions now. We've got up, down, and left, right, and we're going to say for both of those what's positive. And so people often like to use up is positive, down is negative, and then right is positive, left is negative. So this is going to be 8.66 up, which we'll think about from here on also as positive 8.66. Okay, so then what about the other side of the triangle? That's going to require a different trig function. So we could come back in here and say, Well, this also means there's another